This video is about how we control the complexity of the neural networks so that it doesn't overfit, so that it doesn't just try to memorize things but actually learns the pattern of the data. Today we'll decode one of the most common pitfalls in machine learning, that is underfitting and overfitting. So a model feeds data by learning patterns from training examples. So our goal here is to learn general patterns, not just to memorize the training data. So let's say we have a simple two-dimensional data here. We have size and price in these two dimensions, and these are the data points. Our target is to find the general trend in the data. So this is the general pattern this data points follows. We don't need to go through each and every data points. So the quality of fitting determines how well the model performs on unseen data. So if this is my training data and if we try to fit it with a different curves like this that is going through each and every point, so this will work well for the training data itself, but it might not work for the new unseen data. So let's start with underfitting. What is underfitting? Underfitting is when model is too simple to capture the underlying pattern. If you see the data here, this is the general trend of the data. So data points are shaped like a curve here. But if we try to fit the data with a straight line, right? So we'll be missing the trend here, right? So we just lost the data, general pattern of the data. So it performs poorly on both training and test data. So this straight line will not capture the training data, also it will not capture the test data. It will have high bias and low variance. So what is bias and variance? Variance is the measure of how much a model's predictions change when it is trained on different subsets of the training. And high bias means there will be error because model is too simplistic. So in this case, you see the model is too simplistic. So it's not able to generalize the pattern. So that's why we have high bias. Now let's keep aside this bias variance terminologies. We'll just try to understand the basic thing here. So if we have a too simplistic model, then we'll have high training error as well as high testing error because the model will not perform for training data as well as test data both. Few examples, let's say this examples only. We have a non-linear data and we are trying to fit it with a linear model. One more example can be a shallow decision tree that will not be able to capture the pattern of the data. So let's see now the epoch loss curve. So in this direction we have epochs, in this direction we have loss, and we are seeing how the loss is changing over epochs. So in green we have the training loss, in orange we have the validation loss. Our target is to minimize the loss, right? But here in case of underfitting, you see the training loss and validation loss both are not getting reduced, right? So there can be another scenario where this curve, you see, this is oscillating. So the training loss and validation loss, these are oscillating, is fluctuating, like it's not actually reducing. So it is reduced here, again it has increased. So this doesn't represent the training data and test data both. What is proper fitting? Proper fitting is when the model captures the true trend while ignoring the random noise. Random noise means 1 point here and there, that is fine. We are trying to capture the general trend, true trend of the data. So let's say that's why we have added one more polynomial here, and data points with a smooth curve and model passing through the general trend, not every point. It performs well on both training and test data. Balanced bias variance trade-off, and it will have low training error and testing error. Of course, it is trying to capture the general trend in the data, right? So it will perform well for training and test data both, and the training error and testing error both will be less here. In case of proper fitting, you see the training loss and the validation loss both are decreasing, right? So we have a proper fitting here. Now let's see the overfitting. In case of overfitting, we'll have excellent training accuracy but poor test accuracy. You see here, these are the data points, right? And this is the curve we are drawing. So we have added more higher degree polynomials and we get a wiggly curve like this that is passing through every data point. It's visually very chaotic. So of course it is trying to go through each and every data point, so it will do good on the training data, but it will not perform well on a new unseen data or a test data. We have low bias and high variance. What does it mean? Low bias as in the model is not simplistic. It's a very complicated model and it is doing well on training data. High variance because it is not performing well for the new data. So we'll have low training error but high testing error. Low training error because of course this model is trying to capture every noise in the training data, so it will perform well for training data, but it will not perform well for a new unseen testing data. So it will have high testing error. The model is too complex because it tries to memorize noise and random fluctuations in the training data. Examples can be deep decision trees. If we have very deep and decision trees, that will try to overfit the data. Neural networks without regularization. So we'll talk about regularization later. So that is one way to tackle overfitting. But deep neural networks often trained to overfit. So in case of overfit, you see that the training loss is decreasing, but validation loss is also decreasing, but after some point it is again starting to increase, right? So the model has overfit. Now here see the three scenarios represented here. So this is the underfitting scenario. So we have this trained in the data. This is one class and this is another class, but we are just trying to classify this with a straight line. So it is underfitting scenario. This is a proper fitting. This is one class and this side we have one class and this side we have another class. Of course we have some noise here. In case of overfitting, what will happen? We'll get this type of complex graph, right? And it will try to fit each and every data point. So of course it will work well on training data, but it will not work well on test data. So overfitting models are like students who memorize answers instead of understanding the topic. So they do well in practice tests, right? Like training where we know the questions, but they will struggle in real exams with new questions. Now the problem here is why neural network can overfit. Too complex network is often prone to overfit. Too complex network has lots of nodes and weights, and these are the weights, right? Each nodes will be these node connections will have some weights. The weights define the importance of the neurons in the network, right? So this weights here will define the importance of these two nodes. The more complex network with more nodes and weights, the more it will try to capture every minor patterns in the training data set. Hence, it will fail to generalize for new data. Now, what are the major reasons of overfitting in neural network? So, one thing is already we discussed, that is the complex model. So, using a complex model for a simpler problem which picks up the noise from the data. So, let's say we talk about the iris data set. So, if you know about the iris data set, that is a very simple data set. So, if we try to fit this data set with a neural network, deep neural network, so that will try to overfit. One more reasons your model can overfit is small data sets. So, as the training set may not be the right representation of the universe. So, if we have a very small data set, the model will perform well on the small data set. It will try to learn every feature of the data set, but it will not work well for the new data because the training data set we have, that is not a real representation of the overall data. right? So these are scenarios when model can overfit. How do we overcome overfitting? We use regularization. The most common regularization techniques are L1 and L2 regularization. We'll talk about that in our later videos. But this regularization is the main technique we use to cope with overfitting. We apply cross validation. What is cross validations? What we do is we divide our data set, training data set, into, let's say, multiple parts, and then we randomly pick, let's say, three subset for training and the remaining one for testing. So we'll do this multiple times. So next time we might pick this three subset as training subset and this one as for testing. So we'll do this multiple times so that we try to learn the general patterns of the data. Next thing we can do is collect more data. So of course, if the data set is small, it will not represent the whole trend of the data, right? So we need more data in that case. Simplifying the model architecture. So that is one thing we can do to fight overfitting. Use dropout, early stopping, or data augmentations. So these are also techniques like regularization that we can use to fight overfitting. We'll discuss more about this in my later videos. Now, how to avoid underfitting? So first, how do we know there is underfitting? So high training and testing errors indicate the model is too simple or not trained enough. So if we see that training and testing, both the errors are high, then that means that the model is not trained enough. What you can do, you can use a more complex model, switch to a model that can capture nonlinear relationships. From linear regression to, we can switch to polynomial regression or a deeper neural network. We can train for more epochs, give the model enough time to learn the data patterns. Reduce regularization. So regularization is the technique to fight overfitting, right? So if we already detect that we have underfitting, so we have to reduce the regularization or dropout and other things we use to fight overfitting. Add more relevant features. So we can include new meaningful input variables or engineered features that better describe the data. We can ensure the data quality is clean, accurate, and sufficient data that helps the model learn the true patterns. We can use better feature transformations techniques, apply polynomial features, kernel tricks, or modern embedding techniques to capture non-linearities in the data. We can tune hyperparameters properly, adjust learning rate, depth, and other model settings. So there are lots of hyperparameters in the neural network that we can tune for optimal performance. Now, what happens when test fails or test performance is very poor? So if you see the test performance is poor, there can be two scenarios, right? Either the training performance is also poor, then it indicates that there is underfitting. If the training performance is good and the test performance is poor, that means then we have overfitting. So first thing we can do is to check if the training is successful, because even with lesser data, training should be successful first. Then check if there is underfitting, that means training performance is also poor. Then check if the model coding has errors. It might be like there might be errors in the model coding. Check if the model architecture is proper or we need more parameters in the model training. Then try to train for more iterations. Maybe your model needs more time to learn the general patterns. Then change the batch size, learning rate, or weight initializations. All these helper parameters we can change to make the model learn better. So in case we see the test performance is poor, we try to first overfit, and then we can take care of the overfitting. So if the overfit means the model works well on training data. If the model doesn't work well on the training data itself, then there is no point to go ahead, right? First, we have to make sure the model does well on training data. Then we see there is overfitting, then we'll tackle the overfitting. So when test fails but training performance is good, that means we have our training is good, training loss is less, training performance is good. So there can be two scenarios. Training and test data distribution might be very different. So let's say you are training with a different kind of data and testing on a totally different kinds of data. So then of course training performances will be good and testing performance will not be good, right? But the other scenario that we are currently discussing in this topic is about the overfitting. So there can be overfitting. That's why the training performance is good, but the test is not. So we need to use regularization techniques that we'll discuss in our next videos. So those regularization techniques will tackle the overfitting.